Right, hello. Okay, so good afternoon, everyone. Hello, good afternoon. Are you guys around?
Good afternoon,
Good
sir.
Afternoon.
afternoon, sir.
Afternoon,
Good
sir.
afternoon. Okay, so again, may I request everyone to please open their camera so that I can see your faces while I'm discussing. Anyone who's willing to open their camera so that I would know that you guys are around, like because it's always hard to teach if I'm not sure if you guys are really there or no. Only Mr. Soriano. What about the others? Mr. Aizel, Mr. Bautista, Mr. Tanicala, Mr. Nathaniel, Miss Ginoran, and Mr. Macabio. Don't be shy. All right, so there you go. So I hope all of you will participate this one so that it's fair to those two who have opened their camera. Anyway, so all right. So for today's meeting, we will try to finish the module 6 and 7. Okay, since this module 6 and 7 are a super short topic. Okay, and Zener that is quite easy to understand anyway. All right, so are you guys ready now? So just give me thumbs up, just to let me know that you guys are very good, ready, and prepared. Okay, how about Miss Grace? Okay, so I think she's not around, maybe. All right, good. All right, so let's start with the definition of a Zener diode. So, in midterms and then before this module, I have already mentioned a Zener diode a lot. Okay, and then you guys probably already know what or how does a Zener diode work. So Zener diode is a special type of diode which behaves just like a normal general purpose diode consisting of a silicon PN junction and when biased in forward direction. Okay, so it behaves the same with a normal or just like a normal diode if it's in a forward direction. However, as soon as the reverse voltage reaches predetermined value, the Zener diode begins to conduct in the reverse direction. Okay, so the only special thing in here is once a certain voltage reach, let's say this predetermined value, okay, it would start to conduct in a reverse bias mode. So unlike in other diodes that we had before, it it's completely doesn't work. Okay, it doesn't permit a current on that diode. But in here, it will allow to flow a current once it reaches this predetermined value. Okay, and then that voltage is called a Zener voltage. Okay, so this is because when the reverse voltage applied across the Zener diode exceeds the rated voltage. So we actually call that one the rated voltage. Okay, or well, actually can call it the predetermined value or predetermined voltage or the rated voltage. So those two are just the same. Okay, of the device, a process called avalanche breakdown. So once we breach this rated voltage, so what will happen is they call this one avalanche breakdown. Okay, once the permit will now once the current now is permitted to flow on that diode, okay, or that reverse bias connection. So this one occurs in a semiconductor depletion layer and a current starts to flow through the diode to limit this increase in voltage. So in other words, it is especially assigned to reverse breakdown voltage, which takes advantage of any reverse voltage applied to it. Okay. So if you guys are going to take a look on this one, so this one is the graph of of a normal diode. But if you guys are going to include this one, let's say you've already reached the reverse uh, this rated voltage refers a bias voltage. So it will start to conduct now, which is called the breakdown region or the avalanche breakdown. Okay. So here we have here a like a what get this one, a picture wherein we have a this one. It's not a demo, but just to show to you guys that this is how a Zener diode works. Okay, so letter E is a reverse bias SI, small signal diode breaks down at about 100 volts. Okay, so this one, in order for you to make this one work in reverse bias, so you should reach this 100 volts. So that is the rated voltage of this diode right here. Okay, so as you can see, once it enables to reach that 100 volts, and then the rest will now pass through uh, this resistance right here. Okay, so the remaining will be here on the resistance, which is of course 50 volts. Okay, but this is not the correct symbol. It's just saying that yeah, you can have this one as a normal diode, but at the same time, it's saying that this is the start of understanding what a Zener diode is. So the correct symbol for a Zener diode is something like this. So there is just a short, line added. So down here and then up here. Okay. So unfortunately, when normal rectifying diodes break down, they usually do so destructively. Okay. So if this is just a normal diode, so this will maybe it won't explode, but uh maybe it will destroy this part of your circuit. Okay. So it will do so destructively. So however, it is possible to build a special type of diode that can handle breakdown without failing completely, which is now this Zener diode. So this type of diode is called the Zener diode, and its symbol is shown on the figure B above, which is this one. Okay. So this is just the explanation that it works the same with a forward bias. So if it's non-ideal, it will consume 0.7 volts. But if it's a non-ideal, then yeah, it will consume nothing. Okay. But in reverse bias, so that is now where this one is specialized. So once you reach a certain voltage, okay, or reaches or exceeds, so either of those two, we call that one now a Zener voltage. Okay, once it was able to reach that peak of voltage. Okay, so let's have an example for you guys to appreciate what is this Zener diode all about. So here is a Zener diode, and then it has a rated voltage of 5 volts. So it is asking us to find the V out, the total current, during the positive and negative half cycle. Okay, and this one is an ideal Zener diode. So during the positive half cycle, we're going to have here a reverse bias, right? Positive half cycle. Will this become a forward bias or reverse bias? Anyone? What will happen to our Zener diode? Okay. Of course, this will become a reverse bias since positive is connected to negative and the negative is connected to the positive. So as a result, we're going to apply what we have learned in here. So is this voltage input or voltage source enough, to make this one pass through or permit a current? Anyone? Okay. So of course, no, since 3 volts is not enough to make this one work in an avalanche, or is that one an avalanche breakdown or the Zener voltage. Okay. So just imagine that this is one this one is like a voltage threshold, like in a forward bias. If it's non-ideal, it will eat 0.7 volts, right? But in here, it requires a certain amount of voltage, which is 5 volts. Okay, the only difference is if this one is higher, then it will be able to pass through this diode, but it will not hit any voltage, or there is no voltage drop. Okay, so we still have reading here of, let's say if this one 6 volts, we still have here reading of 6 volts. Okay, that is their only difference. Anyway, just to show you guys the solution. So during the positive half cycle, so it's completely reverse bias, so there is no output, and then there is no current. Okay, and then during the negative half cycle, so negative to negative and then positive to positive, so this will function as a forward bias. So we now have here an output which is negative 3 volts, and then for the current we have negative 3 milliamps. So just apply Ohm's law, and then you'll be able to get the voltage output and then the current. Are we clear so far? Mr. Eisel, any question?
No question.
All right. So let's now move on to example number 2. Okay, so in here, it's now very obvious. So if we're going to start with positive half cycle, so this will be in reverse bias, and 14 volts now is enough to pass through this Zener diode since it's more than the rated voltage. So in here, we're going to have a V out of 9 volts. Okay. My bad, my bad. Again. So my first explanation was a mistake. So I really am so sorry for that. So we really need to deduct that rated voltage. Okay. So not just bridge. Okay. And then you should exceed that one. Okay. Because if this one is exactly, let's say, 5 volts. Okay. 5 is equal to 5. So it's like deducting this one. So 5 minus 5 is like having a V out of 0 also. Okay. So it should be more than the Zener diode because you're going to deduct the rated voltage. Okay. But wait a second. So it will be voltage. All right. Okay then. All right. So let's go back here. So in here, we're going to have an output of 14 minus 5, which is now equal to 9 volts. And then for the current, so just use I is equal to V divided by R. So we have 9 volts divided by 1K, we will get 9 milliamps. And then during the negative half cycle, we have here negative 14 volts. So it won't affect, or this rated voltage won't affect our voltage input during the forward bias. So the only time that you need to deduct this one is during the reverse bias connection. Okay, so 14 negative 14 volts output. So divide that one by 1K. So you will get negative 40 milliamps as our current. Okay. So clear so far? Okay. All right. So again, my bad, my mistake with this one. So this one is 9 volts, not 14 volts. So you should deduct the rated voltage. Okay, let's proceed to example number 3. So in here we have 2 Zener diodes. So I would like you guys to figure out what is the value of our V out during the positive half cycle. Anyone? So what is the value of our V out during the positive half cycle?
Is it 30 minutes? Guess lang.
Yes, that's correct. So we have the positive 20 volts during the positive half cycle. But how about during the negative half cycle? What is the value of our V out?
Baliktad lang, sir, negative.
So it will just become a negative 20 volts. Okay. And then for the current, so for the positive half cycle, we have positive 20 milliamps and then negative 20 milliamps for the negative half cycle. Right. So here are the answers. So once it passes through this one, so it will deduct 10, and then it became 20 now at this point. And then at this point, it's now in a forward bias connection during the positive half cycle. Okay, so that is why the reading on the V out is 20 volts. So the same with the negative half cycle. So the first one, so it's in forward bias, but after passing to the second one, it's now in reverse bias. But since this one is Zener Diode, so you just deduct 10, and then it will give you a value of negative 20 volts. Okay, and then for the current, so they are super easy to solve as long as you know the voltage output. So are we clear so far regarding with the example number 3? All right, so let's now proceed to the next one. So in here, this one is still a Zener diode, but this one now is a Zener diode as a voltage regulator. Okay, so we have a lot of say variables that needs to be considered in here. Okay, since this one's like the uh, simple circuit of a voltage regulator. So the first thing that we need to do is first check whether it's operating under breakdown voltage, wherein if it's operating in breakdown voltage, okay, or in reverse bias, VTH should be greater than VZ. Okay, wherein VTH is the Thevenin's voltage. So you will get the idea, or you will get the formula of the Thevenin's voltage. So that's where this one came from. And that one should be greater than VZ. So this VZ is our Zener voltage, okay, or the voltage across this diode or Zener diode. Okay. So in here, there is no other derivation, which is the Thevenin's voltage. So once you're done with the electrical circuits, so just go back with the module of Thevenin's voltage, and then analysis one again, and then you'll be able to come up with this formula. Okay, so we will not explain Thevenin's voltage in here since it's not part of course. Okay, but yeah, this is the formula for the Thevenin's voltage of this one, or after transforming this one into a Thevenin's circuit. Okay, so this one is the same with this one. Okay, so you can use either of those two. Okay, and then we also have IL, or the current across your load resistance. So this one is very straightforward. So it's this Ohm's law. So this one is solvable by the voltage load divided by the load resistance, or the RL also. Okay, or you can use this one also. So IL is equal to VC divided by RL. So this one came from here since again the idea of a parallel is whatever is the voltage that is passing through this, let's say, parallel circuit, okay, or this path right here, is just equal with each other. Okay, so once this voltage source distributed everything, so we have the same reading now for the VZ and then the voltage across your RL. Okay, so that is why VZ is equal to your VL. Okay, so you can use either of those two. And then for the IS, we have here the series resistance, or the series current rather. So IS is solvable by using this formula, VS minus VZ divided by RS. Okay, so that is the first formula that you can use for the IS, or you can also use this one. IS is equal to IZ plus IL. So they were separated into two. Okay. And for the PZ, so it's the idea of P is equal to I times V. So PZ is equal to IZ times VZ. So just get the current of this Zener diode and then the voltage of this Zener diode. Okay. So in here, there are no other derivations with those formula. It's just the analysis with the use of Ohm's law. Okay, and then with the use of a Thevenin's formula. Okay, so those are the things that you guys need to take note when it comes to analyzing this circuit. Okay, well, I think you can also use KVL, but this one is already the simplest form in finding out the RS, IS, VZ, IZ, IL, and then RL. Okay, so let's have an example with the use of those formulas. So find the V out, current across load resistance, current across series resistance, current across Zener diode, and then the power dissipated across a Zener diode. So this one is just the same with this one. It's just that this one now has a value. Okay, so we have 20 volts, we have 150 ohms, we have 8 volts as the rated voltage, okay, during the reverse bias connection. And then we have here a load resistance of 1000. Okay. So since this is maybe your first time seeing this one, so there is no way that you guys will be able to memorize this one in just one reading. So let's proceed to the solution right away. So all you need to do is apply all of these formulas, and then you will get those values. Okay. So when it comes to analysis, it is now completely up to you guys. Okay, just replace all of the given values with those given formulas. Okay, so there is no twist in here. So whatever we have in here, so you can find VTH because we have everything. Okay, everything is already given. So the same with IL. Okay, we also have the VZ. Right, so VZ is 8 volts, wherein it's the rated voltage. IL can be solved using the VZ divided by RL. RL is already here, so no problem with the IL. And then for the IS, we have here VA minus VB, wherein VA is equal to the 20 volts, and then VB is after passing through this RS, which is equal to 8 volts. Okay, so just get the voltage drop is 1, and then deduct that one to our 20 volts, and then it will give us a result of 8 volts. And then divide this one by RS, okay, which is already given, then will give us a result of 80 milliamps. And then for the IZ, so we have two formulas for this one. We have IS minus IL, or you can use, where's that one? IS, wait a second, IS is equal to IZ plus IL, which is already, okay, so we didn't use the IZ plus IL because we don't have the IZ yet. So in here, we've just used the formula of IS is equal to IZ plus IL. So this is where this one came from. So nalipat lang, transpose lang yung IS natin. Okay, wherein the one that we are now finding or looking for is the IZ. Okay, so this one came from this one right here. Okay, so I hope this one is clear, this IZ right here, because we don't have IZ formula in here. But this one was derived from this formula. Okay, and then just substitute everything. So we have the IS, and then we have the IL. Okay, and then give us a result of 72 milliamp. And then for the PZ, so we already have the IZ and then the VZ itself. Okay, so you can already solve that one. Okay, so yeah, this is the basic example of a voltage regulator. Okay, if everything is given. Now, the hard part in here is the example number 2, 3, and then 4, and then 5. Okay, because in here, we're going to make the RL as your variable or as a missing, say, a missing component. Okay, so we wanted to solve the minimum and the maximum value of our RL here, or the load resistance. Okay, so what is the minimum value that we can put in here, or what is the maximum value that we can put in here? With those given values right here. Okay, so in here it's a complete new understanding of the formulas. Okay, so when it comes to derivations, so feel free to read more articles regarding with the RL mean and then the RL max. So basically, we're just looking for two variables in here, RL mean and then RL max. But this one is the formula for the RL mean, okay? And this is the formula. Where is that one? Well, actually, we have a lot of steps that we need to figure out for the RL max. So yeah, we have here VZ divided by IL, but we have to find this IS and then IL mean first, and so on and so forth. Anyway, so since this one is open notes, so wala na kayong problema. Okay. So the only thing that you guys maybe need to figure out is what is the reason why we have RL as a variable, okay? And then what is the reason why we have VS as a variable, okay? And then RS as a variable, okay? So lahat sila meron naman ng mga given formula. So there is no tricky part in here. So as long as you know Ohm's law, so maybe RS is also missing. So as long as you know Ohm's law, then you can just simply apply these things, because yung mga given formulas naman dito is na-form sila using Ohm's law and then other theorems. Okay. Okay, so all right. So yeah, there is a direct message that came from Mr. Jean Alexis. So yeah, it's really true that they are using different variable names like forward resistance or the bulk resistance. But once you understand one article, then I think shifting into another is now an easier thing. So once you've learned the basics maybe, okay, or the fundamentals, then it's now easy to read the other articles. Okay, like the NESO Academy. So yun laging pinagbabasehan ko, NESO Academy and then all about circuits. So those two are using different variables as always. Okay. So they have their own terminologies, but yeah, how they solve it is the same anyway. Okay. So for this RL as a variable, so the one that we are looking for is RL mean and RL max, and then here is a given formula. And then everything is already given. So all you need to do is substitute those given values. So 100 times 5 divided by 15 minus 5 is equal to 50 ohms. Okay. So there is no pattern in here. So this one is quite confusing. So there is no way that, okay, I will solve the RL max first. Okay, I will solve the RL mean first. Okay, so they have their own different, anong tawag dito? Parang kasi marami tayong option. Okay, so as long as you were able to find this maybe given and then they are available, then you can just solve the IS right away. Okay, or once you have this given IS minus IZM, then you can just solve the IL mean right away. Okay, so if you guys are going to take a look at this one, we have RL mean, RL max. Yes, we have VS mean and VS max. But in here, in RS as a variable, they solve first the RS max before the RS mean. Okay, so I could not say that you guys have to find the mean first before the max. Okay, for that given or for that missing variable. So ang advice ko na lang siguro sa inyo is familiarize how did they come up with this one. Okay, so this is the formulas for the process for the RL as a variable, and then this is the formulas or the given or the kung ano man gusto mong itawag or technique, okay, for the VS as a variable, and the same with the RS. Okay, so I cannot find any other convincing anong tawag dito, explanation on why you guys need to memorize this one. But maybe in the future, you'll be needing the the idea on how to get the individual values of this RS, V1 or VS or the RL itself. Okay. Well, anyway, since we don't have enough time anymore, so we'll just continue the the analysis with those solutions on the part 2. Okay. So goodbye for now, and then see you guys later.